So today we're going to be discussing cheletropic processes. These are concerted processes whereby two sigma bonds either form or break at a single atom location, shown here with sulfur and carbon in these two examples. In terms of nomenclature, these are described in terms of N+1 reactions, whereby N describes the number of atoms of the non-single atom species. So over here, we've got a 4+1 cheletropic reaction, where the diene has 1, 2, 3, 4 carbons, which react with a single atom center. Over here, we've got a 2+1 cheletropic reaction, so our alkene has 1, 2 atoms, and it's reacting with our single carbon center. In terms of the single atom species that undergoes reaction, there's a couple of common species that you see a lot. Probably the most topical of these is singlet carbene, shown over here, whereby our single atom is carbon. It does not obey the octet rule, so it has 2 bonds and a lone pair, and as you'd expect, it's quite reactive. Singlet carbene can undergo cycloadditions or cycloreversions during cheletropic reactions, whereas certain other single atom species, such as those that could form gaseous products as part of the reaction, these undergo cycloreversion only, since their products are lost to the reaction when they're formed. So examples might include dinitrogen, carbon monoxide, and similar species. The final common species you see during these reactions is sulfur dioxide, and this can undergo cycloaddition and cycloreversion reactions. So if we consider the frontier orbitals of the single atom species, whereby X is the atom undergoing the reaction, Y and Z are any atoms bonded to that single atom, we can see that we have a filled sp2 orbital as well as an empty p orbital. This sp2 orbital is lower in energy than the empty p orbital, hence why the electrons reside there. And it's both of these two orbitals that are going to govern its reactivity in terms of the localization of electron density in the filled orbitals and the space to accept electron density in the empty orbital. So the first example we're going to look at in depth is the reaction between olefins and a singlet carbene in a 2+1 cheletropic reaction. We can see it's a cycloaddition reaction, we have our double bond, we have our 2 orbitals that potentially can undergo reaction, and it's going to form this 3-membered ring here, with 2 bonds forming to our single atom. For any of these types of reactions, there are 2 ways whereby the reaction can proceed. There is a straight-on approach, whereby our singlet species moves in a linear fashion towards the orbitals of the double bond, and an interaction occurs. So here our double bond is shown in this orientation, and at 90 degrees or orthogonal, we have our single atom species moving towards it in the direction of the blue arrow. We can consider the filled electron orbital, so that would be the highest occupied molecular orbital, and it's going to interact with the lowest unoccupied molecular orbital of the double bond. And in this particular situation, when the filled orbital approaches these 2 orbitals, there's a bonding interaction with one, but an anti-bonding interaction with the other. So the net result is no favourable interaction between these electron orbitals. Conversely, if we consider the empty p orbital of the single atom species, when we move this in a linear direction towards the highest occupied molecular orbital of the double bond species, again we see one bonding interaction but one anti-bonding interaction which cancels it out. So the net result is no bonding interaction seen for this linear, straight-on approach of the single atom species into the double bond. So if the linear straight-on approach doesn't work, what could work? And in that case, it's going to be a non-linear or angled approach of the single atom towards the double bond species. So we've changed the orientation of the singlet carbene. So instead of this filled sp2 orbital directed straight on at this double bond, it's approaching at a downward angle. And as we move it closer to the double bond, we can see that the highest occupied molecular orbital is in the appropriate orientation to interact with the lowest unoccupied molecular orbital of the double bond, whereas the differently phased molecular orbitals are also aligned to interact. So this is going to give a favourable bonding interaction. Similarly, if we move from the sp2 orbitals of the single atom species and we look at the empty p orbital of the single atom species, we can move this as well towards the highest occupied molecular orbital of the double bond, and there are two favourable bonding interactions if we do so, meaning that both the sp2 orbital as well as the empty p orbital of the singlet species, each of those are primed to receive favourable interactions, regardless of which species is in the homo or lumo state. So to summarise, the singlet carbene can approach in either a linear or a non-linear fashion, and the orientation of that species is going to matter in terms of whether or not it receives favourable bonding interactions. And this is useful because we can use that to impart stereo control of the products. So if that was a 2+1 cheletropic reaction, what about a 4+1 reaction? Here we can see the overall reaction structure. We have a diene, 1, 2, 3, 4. We have our singlet carbene here, and we can bring them together to form this 5-membered ring structure. One of our double bonds has gone to form these two new bonds to the carbon, while the second double bond has shifted between where those two double bonds were originally situated. Now, where previously a non-linear approach was required, when we move to a 4+1 system, now a direct linear approach is favourable when bringing our singlet carbene into this conjugated system. Looking at the orbitals, we have our sp2 hybridized bond of the singlet carbene, and it's going to interact with the double bonds in the LUMO state, which puts these outermost p orbitals into this phase or orientation. The way it's drawn, we can draw two bonding interactions with the lower phase of the p orbitals, and if we were to rotate these two outermost p orbitals in a dis-rotatory fashion, we can see that the lowermost lobes would rotate inwards and meet with this incoming sp2 hybridized orbital with the lone pair, forming a bonding interaction and giving us our 5-membered ring. Similarly, if we look at the LUMO state of our singlet carbene, so our empty p orbital, now the double bond is in the HOMO configuration, so we have opposing phases in the outermost p orbitals. Exactly the same situation arises. We're going to get a favourable bonding interaction on either side as we move our singlet carbene directly towards the double bonds. If both of these p orbitals rotate inwards, they are going to meet these incoming empty p orbitals of the singlet carbene and form a bonding interaction. And indeed, this is a general rule. A nonlinear approach is generally favoured for a cheletropic reaction that involves a 4n system, and the p orbitals in the double bonds are going to rotate in a conrotatory fashion to intercept the orbitals of the single atom species. Conversely, a linear approach is generally favoured for cheletropic reactions involving a 4n+2 system. So here we have a pair of double bonds, and these outermost p orbitals of the double bonds are going to rotate in a disrotatory manner to intercept the orbitals of the single atom species. So here's a general reaction example that involves cheletropic reactivity. We have this starting material, there is a pair of double bonds on this side that could react with our single atom species, and when we apply heat, a cyclization occurs giving us this product. So the first two steps of this reaction are all about generating our carbene. So the first step is loss of nitrogen. This generates an acetone leaving group, and when that departs, we arrive at our singlet carbene species. And as I mentioned before, we've got this conjugated pair of double bonds on the other side of the molecule that could partake in an intramolecular 4+1 cheletropic process. If we then draw out our products, we see that there's two possibilities whereby our single atom could form two new bonds with these double bonds, with the diene located at the other side of the molecule. Going back and looking at our product, we can see that only one of these actually occurs. The conformer on the left is what we see, conformer on the right is not seen. And the reason for that probably comes down to the sterics of the transition state. So drawing out this chain, we can see that the methoxy group is situated kind of equatorial, so placed away from the transition state, whereas on the other side, the methoxy group is kind of axial to the transition state. Here I've included the LUMO and the HOMO orbitals of both potential products. And we can see on the left-hand side, there are favourable interactions where we have this cis conformation of the methoxy group, whereas we don't see this trans conformation of the methoxy group, implying that it's not favoured. And to me, this says that in order to situate this methoxy group above the rings in the transition state, it likely shifts the orbitals of the single atom species lower, preventing this favourable interaction I've drawn here. I did have a quick look in the literature, and in some of the publications where these types of reactions occurred, they did indeed draw attention to the orientation of these sp2 hybridized orbitals of the single atom species and their alignment in relation to the orbitals of the diene. So it's likely that these subtle steric effects are important in terms of directing what products you actually see in the reaction. Moving on from carbenes to sulfur dioxide, this will contain our sp2 hybridized lone pair situated on the sulfur, and there is also 4 pi electrons. 1, 2, 3, 4, given the negative charge. Given there's 4 electrons in our pi system, we can predict what the orientation of the p orbitals will be. So lowest energy, 2 electrons filling this orbital, next energy band, where our p orbitals have opposing orientation, 2 electrons go into this orbital, and then finally there's no more electrons to put in the uppermost energy orbital. So in terms of the highest occupied molecular orbital of sulfur dioxide for these p orbitals, it's going to be this arrangement of p orbitals shown here in the middle. 1 up, 1 down. So the typical cheletropic reaction of sulfur dioxide is either extrusion, where you lose sulfur dioxide, where sulfur dioxide is added to a double bond system. These reactions are stereospecific and they're also reversible. The 2 bonds that form to the sulfur occur in a suprafacial manner, meaning on one side of the molecule. Now, in these reactions, our sulfur dioxide will approach in a linear fashion. So we can first consider the p orbitals of our sulfur dioxide. Going back, our lowest unoccupied molecular orbital for the p orbitals is this alternating down, up, down orientation. So if we apply that to our sulfur dioxide, we see that this arrangement is perfect to interact with the HOMO orbitals of our double bond, provided the sulfur approaches from either the underside or the top side. So this is where our suprafacial reaction comes into it. It's not going to react with the lower half on this side and the top half of the other side. It's always going to be both the lower halves of the p orbitals or both the top halves of the p orbitals. If we instead consider the HOMO sp2 hybridized orbital of the sulfur dioxide, so our lone pair here, we can see that again this is perfectly set up to react with the LUMO orbitals of our double bonds by simply approaching the bottom half of the outer 2 p orbitals. This allows us to then see how these outermost p orbitals of our double bonds are going to rotate to meet the orbitals of our single atom species. And the left-hand p orbital is going to rotate counterclockwise. The right-hand p orbital is going to rotate clockwise. So this is a disrotatory reaction mechanism. And this rotation of the outermost p orbitals is what gives us our stereospecific response in the product. So counterclockwise, clockwise is going to cause both of our methyl groups to rotate downwards, giving us this arrangement shown here. So if this trans arrangement in our starting material gives us this final diastereomer, what happens if we have a cis arrangement in our starting material? So we can redraw out our transition states. Exactly the same thing occurs, except now our methyl group is situated over here, and it's going to rotate upwards in a counterclockwise fashion, and we get this reversion in stereochemistry on this side. And this is what gives the stereospecificity to this cheletropic reaction. So what about for an alkene? Well, for this reaction to work, we need the sulfur dioxide to approach in a non-linear fashion. Once again, drawn out the HOMO and the LUMO orbitals for our double bond and our sulfur dioxide. Instead of approaching directly, the sulfur dioxide is approaching in a side-on fashion, allowing this favourable interaction with the HOMO orbitals of the double bond. Arguably, it's clearer if we consider the HOMO sp2 hybridized orbitals of the sulfur dioxide. So in this fashion, the sulfur dioxide very much needs to be side-on to our double bond in order to get this favourable interactions with both phases of the p orbitals. So we get 2 favourable bonding interactions between both p orbitals of the double bond. Here's a quick example of a named reaction involving extrusion of sulfur dioxide in a cheletropic manner. And the interesting thing about this reaction is it's capable of generating quite strained ring systems, which ordinarily would be a challenge to effect. So we start with this tricyclic material. We add a base, which is going to deprotonate at this position. That electron density can form a bond below the sulfur dioxide and eliminating the bromide. And the final cheletropic reaction breaks these two sigma bonds to our sulfur dioxide, giving us this highly strained tricyclic species shown here. So to summarise cheletropic N+1 processes, these reactions govern the addition of singlet carbenes to alkanes, the addition or extrusion of sulfur dioxide, as well as the extrusion of any small molecule leaving groups that can form stable gases. The appeal is that they offer a precise and stereospecific way to form or break two bonds simultaneously to a single atom, and the stereochemistry of the alkene is retained in the products, which enhances the usefulness of these reactions, including for strained ring systems. That's all for today. Thanks for watching.